Hello everyone, welcome to the video lecture on refrigeration cycle. In the last class we talked about the ideal vapor compression refrigeration cycle as well as actual vapor compression refrigeration cycle. Today we are going to talk about the heat pump. So heat pump are generally used in domestic application, and they're very expensive, and also their installation cost, like initial cost, is higher. However, the billing cost of those heat pumps are relatively smaller. That's why in United States, one third of the household, they're adopting this heat pump for their heating and cooling application. So let's take a look. What is the heat pump actually? So in the vapor compression refrigeration cycle, so in the last class we talked about vapor compression refrigeration cycle, right? VCR. In the vapor compression refrigeration cycle, we saw that four basic unit is the compressor, condenser, then expansion valve and a evaporator, right? So evaporator is basically creating the cooling effect, right? So this is the cooling effect. How? It's basically absorbing the heat from the refrigerated space and getting that vapor is basically, or that liquid is, it's basically converted to the gas, and that gas is basically pumping through this compressor. So that's the cooling effect. That's the place where the cooling effect is producing. Now let's take a look at heat pump. So heat pump is also has a compressor, right? Basically this compressor is handling the gas or vapor. So what is happening here, there is a valve, regulating valve or reversing valve. So this valve can change the flow direction. Right now, to get the cooling mode or to create the cooling effect, we are putting this evaporator inside the indoor. Okay, so what is happening, when the gas is expanding through the expansion valve with high pressure as well as high temperature, then it's going through the evaporator, and in that evaporator it's basically absorbing the heat, which is QL. Okay, and then it's absorbing the heat and getting evaporated or getting the gaseous form and pumping through this compressor, and again it's coming through the outdoor where it's rejecting the heat, which is QH. Okay, so now what if we just change the flow direction? So this is, right now it's producing the cooling effect, right? It's producing the cooling effect at indoor just by absorbing the heat of QL. However, if we change the flow direction right here in this place, it will give us the heating effect. How? Let's take a look. So now we can see that if you take a look in between these two, from the compressor to this is the condenser, right? Condenser, compressor to condenser. However, if we change the flow direction, in flow direction means that compressor to, instead of condenser, it will be the evaporator, right? Evaporator. So now you see that it's not going to the condenser, it's going through the evaporator, and then basically that evaporator is it's kind of converted to the condenser, right? Just by changing the flow direction. Now you can see that this, instead of taking the heat of QL, it's rejecting the heat of QH, right? It's creating the heating effect in this space. So it's creating the heating effect. So that's the alternation between the heating effect and cooling effect in between the evaporator and condenser. So basically in this cycle it was the condenser right here outside. However, in this cycle we just change the flow direction, and then evaporator become the condenser, and that's why it's rejecting the heat, which is producing the heating effect, and this one is it's absorbing the heat, which is QL. Okay, so now just by simply changing the flow direction, we are creating the heating effect, and we are creating the cooling effect as well as and also we are creating the heating effect. So that's the working principle of the heat pump. So within a one single device or one single system, you can produce like heating effect and cooling effect, right? So one single system can produce heating effect and cooling effect. So main thing or key component, right? So key component is the valve, reversing, excuse me, reversing valve, right? So that valve is basically regulating the flow direction and creating the cooling effect and the heating effect. So that's the heat pump system. Now let's take a look at innovative vapor compression refrigeration system, another topic. What is that? So in the vapor compression refrigeration cycle, we saw that simply it consists of a compressor, and we saw that it has the condenser, expansion valve, and you also saw that in ideal cases we have a evaporator, right? So in this single system, in actual case, to create the cooling effect, it's very expensive. Number one, expensive process, right? Expensive to create the cooling effect, desired cooling effect in many in the domestic application, or in as well as the industrial application, right? So what happens is that instead of evaporator, we use a heat exchanger, especially for industrial application, where you need really large or high capacity cooling system. Industrial application, where you need high capacity cooling, high cooling capacity. For high cooling capacity, you need high compression, or you need the high compression system. So for high compression system, I mean, to create the cooling effect or high cooling capacity, if you run through a single compressor, the cost of operating the compressor it's going up, or it's very expensive. To minimize that cost, we use a double compression system or two-stage compression system, right? Compression 1 and compression 2. So in that case, it's compressor A and compressor B, right? So and then those compressor are connected by a heat exchanger. So that heat exchanger is basically working as a evaporator as well as a condenser. So for the top one, for this cycle A, we can see that it's working as a evaporator. Basically it's absorbing the heat, while the condenser or the bottom cycle, this heat exchanger is working as a condenser, where it's rejecting the heat. So basically if it rejects the heat Q, if it rejects the QH, and then it will absorb that QH, which is equals to QL. So QH and QL would be the same in this point in ideal case. Okay, so now other than that, this system consists of pretty much all of the similar component: evaporator, condenser, compressor, and expansion valve, right? So in the TS diagram, if we look at this the top cycle, then we will see that this the TS we will see that these this TS diagram, it's very similar to the actual vapor compression refrigeration cycle, right? Ideal vapor compression refrigeration cycle. So in now we can see that from 5 to 6, it's a compressor, which is basically increasing the pressure and temperature, right? And then 6 to 7, it's excuse me excuse me 6 to 7, it's basically the heat rejection, right? QH. So here is the heat rejection QH. And then 7 to 8, expansion valve, right? basically temperature and pressure both is falling, and then 8 to 5 it is heat absorption, right, QH. So here now if you look at this bottom cycle, right, which is the B, from 1 to 2 is the compression, and then 2 to 3 is it's basically constant pressure, 2 to 3 constant pressure heat rejection. So we can see that this cycle is rejecting the heat and the top cycle is accepting that heat, right? So and then 3 to 4 is again expansion valve, temperature and pressure is falling, and then 4 to 1 it's basically the heat absorption. Now we can see that from this diagram, this mass of 6 to 2, how much if we have like this is the compressor B and this is the compressor A, then we can say that we can save the compressor work. Basically compressor is a work consuming device. We can say the compressor work is equals to WA minus WB. So we can save this much of compressor work, right, while we are producing while we can increase this cooling effect, like compared to the top one we can increase this much of cooling effect. So that means if we have like this type of configuration, or if we have like multiple compressor, then we call this type of system is the cascade refrigeration system, right? So for example, or so this would be cascade refrigeration system. So the definition of cascade refrigeration system is nothing but that two or more refrigeration cycle consist of two or more refrigeration cycle, right, cycle, and operates in series. This is important. They are not operating parallelly, they are operating in series. That means that one cycle is depending to the another cycle. Okay, they're running simultaneously. That's basically the definition of the cascade refrigeration cycle. And in cascade refrigeration cycle we saw that it's basically reducing the compressor work, right? One important thing, reducing compressor work, but increase cooling capacity. Okay, so that's the benefit of the cascade refrigeration system. So if we use multiple compressor or multiple two or more compressor in a series connection, then they called cascade refrigeration cycle. And we saw that how it's basically heat rejection and heat addition is happening in this point. Okay, so now let's take a look another refrigeration system, innovative refrigeration system. So for example, in cascade refrigeration system, or one small unit refrigeration system, we usually use the same working fluid, right? However, in the cascade refrigeration system we saw that instead of mixing them, we are just passing through them in a heat exchanger. So there is no mixing here. So excuse me, no mixing right here at this chamber. Okay, they're separate. However, in this another method, it's called multi-stage compression refrigeration system, multi-stage compression refrigeration system. Okay, so in this multi-stage compression refrigeration system we can see that it's similar to the cascade type. However, in instead of heat exchanger we are using a flash chamber, meaning that basically mixing is happening, right? In flash chamber, mixing happens. so the mixing is happening. So here it's also working as a, it's a mixing chamber. So in this one, it's very similar to this cycle. However, in previous cycle or previous one, we saw that this line there was two different pressure line, right? They're operating two different pressure. However, in this multi-stage compression system, we can see that they're sharing the same pressure line. Why? It's because of their mixing in the flash chamber. So we can see that they're sharing the same pressure line, right? So again, in this system, we can increase this heating capacity by this much, right? And also we can save this much of work, right? So if you have, like, this is a low pressure compressor, LP, excuse me, this is a low pressure compressor and this is high pressure compressor, right? So basically this is high pressure and this is low pressure. Then we can save the work, right, in the compressor. So minimize the compressor work, minimize the compressor work, which is input, right? So if we can decrease the input, then obviously we can increase the coefficient of performance, right? And also as well as decrease the cost, right? And increase the cooling capacity. So also decrease the cost, increase the cooling capacity, So that's the difference between, only one difference between the multi-stage and cascade type. So if I ask you in the quiz what is the difference, you should say that instead of heat exchanger it uses a flash chamber, right? So that's the difference between the multi-stage compression. Okay, one more thing here, 9 to 2, this point is also a it's also working as a regenerator. It's basically in the vapor power cycle or the gas power cycle, we saw that the regenerator unit. So this point is also working as a regenerator. Okay, other than that, all the components are similar to the ideal vapor compression refrigeration system, as well as the cascade type refrigeration system. So only one difference is that instead of heat exchanger, we are using this flash chamber. Okay, so another innovative method, it's called the another innovative method is the multi-purpose refrigeration system with a single compressor. So for example, in many domestic application, we need, like, we call it deep freezer, right? So that has really low temperature, and we also need refrigeration unit that relatively high temperature, high temperature compared to this the freezer, this deep freezing unit. Okay, so this is called multi-purpose refrigeration system with single compressor. So this topic is itself, it's telling us that what are the key components. So basically, multi-purpose refrigeration system, right? So we want to use them for extremely low temperature, we want to use them relatively low temperature, and then also it will serve, we want to complete this cycle by using a single compressor, right? So if we take a look at this one, only the key difference in this cycle, or key component, I would say, is the expansion valve, right? Why? After this condenser, we are expanding that gas just to fall the temperature and pressure, and basically creating the cooling effect by absorbing the heat in this refrigerator unit, right? However, still it has some pressure and temperature. If we further expand that refrigerant, then we will get, still we can create more cooling effect. So that's why we are expanding through another valve which is 5 to 6, and then absorbing the heat, basically QL, for the deep freezing unit. And then it's basically becoming very low temperature refrigerant, as well as by absorbing the heat, it's basically becoming the vapor. So again, it's once it's becoming the vapor, or it's converting to the gaseous phase, it's coming through the compressor and running the cycle. Now if you take a look in this diagram, I mean, if you feel like, okay, I'm not gonna run through this refrigerator unit, simply you just add this expansion valve through this expansion valve, basically to creating the you are expanding the same liquid or the same refrigerant in multiple expansion valve to to fall the temperature and pressure really low, then, and it's passing through the freezer unit. Basically it will give you the relatively high cooling effect. So now let's take a look at the TS diagram, what is happening. So 1 to 2, we know that this is the compressor, right? Temperature, pressure is increasing. 2 to 3 is constant pressure, heat rejection, right? Here constant pressure, heat rejection. Now 3 to 4, it's basically the expansion valve. Now if we use the double two expansion valve, then it will 4 to A as well. So this 4 to A, this one, right? And then it's basically creating that heat addition, which is A to 1, right? A to 1, and creating the heating cooling effect in this freezing unit. However, if we feel like, okay, we want to go through this 4 to 5 and condition this refrigerated space, then it's basically absorbing the heat QL of refrigerator 4 to 5, and then 5 to 6 is another expansion valve. So it's it's relatively simpler refrigeration unit or multi-purpose refrigeration system with a single compressor, right? So we can create the cooling effect in multiple places just by utilizing the multiple expansion valves. So that's the purpose of this refrigeration cycle. So another, I think this is the last one, last refrigeration cycle. It's called the name of this refrigeration cycle is the Linde Hampson cycle. Linde Hampson cycle. So basically this cycle, it's completely used for industrial application, right? Industrial and research type application. Why? So for example, in many industrial application, basically we need the refrigeration system like below minus 100 degrees Celsius. So how can we reach such extremely low temperature, right? So, and also, where are these applications? So for example, if you, to give you for research application, to give you an example, the critical temperature of helium and then hydrogen and nitrogen, it's basically minus 268 degrees Celsius, and this is minus 240 degrees Celsius and minus 147 degree Celsius. That means that you will not see the liquid form above or above this temperature, right? So basically, to get the gaseous form, if you ever get a chance to work with all of any of this, I usually work with this one, liquid nitrogen. So when we basically open from the tank, it start to boil at room temperature, or even 0 degrees Celsius, or really low temperature. Why? It's because it has the critical point is minus 147 degrees Celsius, which is in gaseous phase. Now as soon as it's see the room temperature, and it starts to boiling, right? So a lot of industrial application to preserve a lot of chemicals, or to preserve a lot of materials, we need to go down really low temperature. So in that case, how we can achieve such such a low temperature. Of course, if we want to use this domestic refrigeration unit, then it will gonna be very expensive, right? So in such case, we use this type of like modified refrigeration cycle. We call this name of this refrigeration cycle, it's Linde-Hampson cycle. So basically you can see that this compressor itself, it's a multi-stage compressor, right? So basically if we can compress that liquid or refrigerant in multiple stages, then basically we can create this such a low temperature cooling effect, right? So that's the kind of the working principle of the Linde-Hampson. So basically the key component I would say is the multi-stage compressor. So now let's take a look how it works. So 3 to 2, basically we know that it is increasing the pressure, right, as well as the temperature. Now you can see that here 2 to 3, this is compressor 1, this is compressor 2, this is compressor 3, this is compressor 4. So basically multiple compression is happening, right? Multiple compression is happening here. And then from there, from 3 to 4, it's basically the heat exchanger where the heat rejection or the QH is happening, right? And then from the 4 to 5, another additional heat exchanger is or it's a regenerator unit. So basically the Q regen, right? Q regeneration is happening. Now so for such a high temperature and high pressure refrigerant, once we expand through this expansion valve, it will basically convert it as a liquid, or it will basically created that the cooling effect, right? So basically it will absorb that heat QL, and then that liquid is removed from this cycle, and then basically it will be converted as a we'll use the converted as the vapor, and then vapor will be recirculating or we will be using throughout this cycle, right? So now in this case we see we don't usually use the refrigerant 138. We use like ammonia or like water as a refrigerant, right? However, in this one important thing about this cycle is that we are not using the same amount of a refrigerant or circulating through this one. No, in this case we are some of them are rejecting to the environment, right? Or basically if it is a water, we are just rejecting it, and then we're taking the fresh water and also some sort of like fresh makeup gas, to continue this cycle. So it's kind of closed system but not completely closed system, okay? So that's all about this Linde-Hampson cycle. So we know the difference between all of those refrigeration cycle, meaning that what is the difference between cascade and multi-stage, what is the difference between the multi-purpose and Linde-Hampson, right? So that's all about today's topic. We'll go ahead and solve a math problem. Thanks for watching this video.